Hello and welcome to our today's webinar about the optimization of the thermal comfort and atriums with the help of cloud-based CFD. My name is Milad and it's a big pleasure for me to be your today's host. In the past 15 years I've gained a lot of knowledge and experience in different industries using computational fluid dynamics and engineering simulation in general. And as a part of my role as a product manager at SimScale, I try to share this knowledge with new users like you, and therefore I'm organizing and conducting several webinars and workshops around different topics. And today I would like to introduce you to a very popular application of SimScale, and it's the optimization of thermal comfort inside of buildings. And therefore, let's first of all take a look at our today's agenda. We will start with a crisp and short introductory part, where we will first of all talk about the benefits of using simulation in general, and also about the specific benefits of using simulation for projects from the field of AEC. After that, I will introduce you to the SimScale platform. And this will be a very short part of the presentation. I just want you to understand what is the big difference between a cloud-based, web-based tool like SimScale and traditional on-premise solutions. And after that, we will start to dive into our today's topic. And therefore, we will discuss how simulation can be used for projects from the field of AEC and thermal comfort optimization. And we have prepared a live demo, which is actually a simulation project with a real geometry from let's say real world customer. And based on this project, we will show you how you can analyze the simulation results and how they can help you to improve the design and get design confidence. If you have questions during this webinar, don't be shy. You can reach out to me live using the so-called question toolbox, which is inside the GoToWebinar menu, which should be at front of your desktop right now. And just write your questions there, and I will try to answer your question directly on the fly or latest during our Q&A session at the end. All right, and now let's start and dive into our topic. And first of all, as I mentioned, I would like to talk with you about the benefits of simulation. And there are a lot of different ways to explain what simulation actually is and how it can help engineers. And I would like to start with an example, which you can see on the left side of your screen. This is an image showing the facade of the University Hospital of Aachen, which is one of the largest university hospitals in Europe. And there is a quite interesting story about this building. It was designed and constructed more than 40 years ago. And back then, we were like simulation tools were in their childhood and not available at all to the construction or building industry. And yes, so they used a very traditional way of designing all the building, which is mainly based on hand calculations and table book calculations. And in the end, what happened, to make it short, is that, as you can imagine, the HVAC system inside this hospital is very important, because on the one hand, you need to make sure you have, the right flow conditions inside the surgery rooms, etc., and the operation rooms. And on the other hand, you also want to have a good thermal comfort for, the sick people which are in the hospital. And what happened in the end is that after several weeks, they found out that the HVAC system they integrated into the building was much too small. It was really underdimensioned. And in the end of the day, there was nothing they could do around it, because there was no more space planned inside the building for larger ducts. So what they had to do in the end is to build and design and build a separate, second, independent HVAC ducting system around the building, which was something like an exoskeleton. And it actually looks a little bit weird when you really see it, but it actually is very famous right now, and something a lot of people know when they talk about this building or about the city of Aachen, that they have this famous building. And this would not been happened with the aid of simulation. And this is a good example when simulation is important, because actually the engineers, when designing the first internal HVAC system, they were following all the guidelines. And what happened in the end, that a lot of small things summed up, and the global behavior of the system changed, and this was something which was not considered in the tables they used for calculations. And if they had simulation back then, immediately at the very early design stage, they would be able to find out that their first solution will not work, and this would have saved them a lot of money and time. And that's the great thing about engineering simulation in general. It allows you, and I love this sentence, to make designs better and decisions earlier. And in the end of the day, it also helps you to save a lot of money, and it can be used from a different point of view, or let's say it's a very interesting tool for different roles. On the one hand, it's interesting for the designers and architects, in a very early design stage, where they can compare different designs, play around, and get immediate feedback. And when it comes to the engineering part of the project, it can massively help to accelerate test and validation cycles and save physical prototyping, which is for sure in the AEC or building industry not possible, but in a lot of other industries it can really help to reduce prototyping. And there are a lot of different benefits of using simulation, and I would like to summarize the most important aspects for you. And if you put it into a nutshell, you can say simulation helps you with three things. First of all, it helps you to reduce your time investment. It's not only because preparing a simulation is much faster and easier than compared to preparing a physical test, but also it accelerates your design process because you don't have to wait so much, and you can therefore test more design variants and design concepts in the very early product stage. And in the end, it will help you to come up with the best solution in a shorter time. And something which is very much, let's say, connected to this is that simulation also helps us to reduce the costs. Again, it's not only because simulation is cheaper than physical prototyping, but also it provides us with, let's say, a different kind of insights to the results. And usually simulation gives us a better answer, not only what is happening, but why it is happening. And for sure, simulation only helps to minimize failures. And when it comes to the AEC industry, usually when we talk about failures in terms of HVAC ducting, this means that we cannot fulfill the criteria of thermal comfort or something like this. And obviously this is something which won't happen anymore on surprise, because simulation will tell you very precisely how your system is going to perform. Overall, it helps you to make sure that your designs are tested correctly, and it helps you also to improve the efficiency of your designs. Yes. And when it comes to the AEC industry, there are a lot of different applications. And today we will focus only on one aspect, on thermal comfort. But besides this, there are a lot of other fields and disciplines where simulation is actually used by SimScale customers and users to optimize their building project. And the first thing I would like to mention is that simulation allows us to validate and optimize HVAC systems and single parts. So we can not only improve the efficiency of the performance of a fan, of a blower, or of a ducting segment, but we can also simulate the full system and even how it is interacting with the environment and the rooms inside the building. And this can be used, for example, to improve the energy efficiency of our system. And today we will also talk, during the live demo, we will also focus on energy efficiency too. And yes, this is a very interesting way of really squeezing out the best performance you can get from your building design, because usually the standards like ASHRAE we are using to certify our buildings, they are, let's say, very conservative, and usually there is still a lot of performance which can be gained. Besides everything which is happening inside the building, we can also simulate how our building is interacting with wind. So simulation can be used to analyze building aerodynamics, which is very important whenever we have large or tall buildings where we need to take the wind loads on the facades into account, and also for other applications like the optimization of pedestrian comfort in large cities and urban regions. And as I mentioned, we can also use a simulation for optimizing thermal comfort. This is actually very similar to HVAC systems. And the only difference is that when we talk about HVAC systems, we're usually focusing on the ducting work and everything. And when it comes to thermal comfort, we are more focusing on the rooms which are supplied with fresh air by the HVAC system. And finally, we can also for sure do some more advanced analyzers in the field, from the field of air quality control and contamination management. And now I would like to talk with you about SimScale. And first of all, from what I've told you so far, you must think simulation is such a great tool, and it seems very obvious that it's used by a majority of engineers. However, that's not true. Actually, only less than 5% of engineers have direct or indirect access to simulation technology. And there are a lot of different reasons. And 6 years ago, when SimScale was founded by students from the Technical University of Munich, our vision was to enable every engineer in the world to access this technology. And back then, we identified 3 main barriers, which are the reason why only a minority of engineers is using simulation so far. And maybe one of the first barrier which comes to your mind, the first problem for sure, is related with the high cost simulations are associated with. So usually if you wanted to start with, or if you want still to start with an on-premise simulation solution, you usually need to spend like a huge amount of money, 20,000-30,000 euros in advance just to buy the right hardware. You need a powerful workstation, you need some powerful service for the computations, you need the software license, and in the end of the day, you will end up in spending, I don't know, 30,000-40,000 euros without having run even one simulation. And especially if you think about small companies or companies who just want to use it for one project for a, let's say, limited time, usually that doesn't make sense. And also consultancy is much too expensive for those kind of customers or users. The next big problem is what we call the access barrier, because even, let's say, if you get the hardware and software for free, it's not like you just plug it into the, you just plug and play it and you can run simulations. You need to install the software, to install a license manager. You need to make sure that everything is connected, that you have network devices, network storage, and usually for this you need really a specialized IT guy who's focusing only on that. And the third reason, and from my point of view the most important reason, the big majority of simulation tools in the past were designed for simulation experts, but not for designers, engineers and architects who want to apply this as a tool. And these are the 3 things we wanted to make different, and that is our solution. SimScale, the world's first web and cloud-based simulation platform. So what does it mean? In a nutshell, it means that to access SimScale and, let's say, unlimited number of simulations, the only thing you need is a computer, and it doesn't matter if it's a high-performance workstation or a very old and cheap laptop, a working internet connection and a standard web browser. That's it. And then you can access the SimScale 3D simulation platform through your web browser. All the storage, simulation tools and licenses will be provided through the cloud. And that means that SimScale gives access to everybody to the world of simulation. And I just want now to talk with you about some of the major unique, one of the unique features of SimScale. So first of all, SimScale is what we call the all-in-one tool, which means you don't need to buy a special license for if you want to simulate structural mechanics, and another one if you want to do fluid dynamic. Every user can access the same solvers, the same technology. And besides, the SimScale is super fast and easy because it's cloud-based. So usually simulations can take up to weeks on local devices. And with SimScale, you can use up to 96 cores, which allows you to get your results very fast and also on every device you want. SimScale also provides a new approach to support. We have directly integrated into our simulation platform. We have a chat so you can interact with our support engineers, support team directly out of the platform. You can also call our user success team and contact them by email. Besides this, we also offer consultancies, webinars, and trainings. And that's what I love the most about SimScale. SimScale has this super nice pricing. And actually, we have a freemium pricing model, which means you can start to simulate from free. And as long as you simulate for free, your simulation projects will be public and become part of our simulation library. But based on your needs, actually, you can choose if you want to pay or not. And we offer a lot of nice collaboration features. We have a SimScale community with more than 100,000 of engineers. And yeah, there you can just connect with other people and share your know-how on project. And also SimScale is cloud-based. It's super high secure since we're using different kind of encryptions at the different stages of our product. All right, and now let's talk about how we can use CFD simulation in order to improve thermal comfort. And one thing I would like to talk about is how CFD can be used together with ASHRAE or US Green Building Council standards. And in the past, there were a lot of different standards for different applications. So there was like the ASHRAE 55 standard for thermal comfort and a lot of other ASHRAE standards for other applications of indoor flow. And in the past, it was also like that a lot of standards were existing under different names. Like ASHRAE 55, there was also like European version called ESN, ISO EN, and there is something new around. It's called ASHRAE 189.1, and it's actually a joint standard which was developed together by ANSI, ASHRAE, the US Green Building Council, and it will be the successor of a lot of different old ASHRAE and old ANSI standards, including ASHRAE 55. And there are actually a lot of aspects of ASHRAE 189.1 which can't be considered with CFD. And actually, that's the majority. And I just want to give you some examples because there are a lot of misconceptions around this. For example, if you want to simulate the water usage, fluid flow simulation will not help you because the water usage is depending on the number of residents or people working in the building and on some local factors on which kind of sanitary equipment is used. The flow itself inside, let's say, the flush or the piping system has not really a direct influence on the water usage. The same with surface finishes. I know that it's something which comes or somehow related to engineering, but these are all things which are part of the standard which cannot be considered using CFD. But in contrast to that, there are some significant parts of the standard which are associated with airflow. And these are things we can simulate, including thermal comfort for human occupants. This is what we will focus today. But also including ventilation for acceptable indoor quality. And there we are talking mainly about, stains, stuff like air exchange rate and stuff like that. And also you can use it for energy consumption and efficiency. Okay, and before we start to take a look at our today's live demo, I would like to introduce you with a very simple theoretical concept of CFD and how it can be applied to thermal comfort simulation or HVAC simulation in general. Whenever we want to simulate ventilation, there are two scenarios and they need different kind of modeling strategies. Let's start with natural ventilation. Whenever we have natural ventilation, our domain is actually just made of two things. We have our domain itself, which is a part of the fluid which will be calculated or simulated by the tool. Inside, we have our building, and this building has openings which allow the ambient air to flow in or outside. And inside the building, we have what we call abstractions, which can be objects like occupants, walls, tables, whatever you think about, depending on your level of detail you want to go with. And I actually have just two kinds of boundary conditions to describe how our building is interacting with the environment. One is expressed by the flow conditions, which is the velocity and the pressure. And usually here, for natural ventilation, we use the atmospheric boundary layer boundary condition, where we will grab the wind speed statistic, wind speed data from a database and use it to, for example, if it's coming from the west side, we would make this wall here the inlet, and these are the walls the outlet. And we can use, but this is only optional, thermal conditions if we want to include the effect of natural convection. If we want to do mechanical ventilation, and this is something we want to focus today, so then we have a little bit different simulation model. First of all, we don't need to consider the environment, therefore our model only includes, let's say, the inner volume of the building. Again, we have obstructions, but this time, instead of openings, we have supplies or exhausts. At a supply, we can supply fresh air. At exhaust, we will remove the old air. And again, we have flow conditions and thermal conditions, but in addition, we can also use passive scalars if we want, for example, to track the contamination inside the air or the transport of yes, passive quantities and scalars like fog, for example, or CO, carbon monoxide. Yes, and now let's take a look at our today's topic. So today we want to apply CFD to optimize the thermal comfort in an atrium. And on the left side now you can see a simulation or a visualization of the simulation results we created. And this is the atrium we want to optimize. So we have, we can see the streamlines here, how the air is leaving the different outlets and inlets on the different levels. And so first of all, let's think about what are our design constraints this time. And actually, there are a lot of different things we can do. And depending on the stage of your product, you can really start with fundamental analysis, comparing different designs for the whole atrium. You can also play around later then with the number and location of inlets and outlets. And you can also play around, if you want, with the flow rates and temperatures at the inlets and outlets. Besides that, our system is let's say, constrained by the occupants because they're releasing heat. They have a metabolic heat rate. And whenever it comes to understand the comfort of the occupants, we also need to know which clothing insulation should be considered. And for sure, all the time, we need to make sure that our simulation, our building is in compliance with ASHRAE 55, or ASHRAE 186.1, how it's called today. Yeah, and now let's talk first of all about the project. So the first thing you need to, if you want to do such a simulation, is you need to have a working CAD model. And usually it does not make any difference which CAD tool you're using. Some of our customers are using Rhino, some others are using Revit or AutoCAD. And SimScale actually offers a lot of different options for file import and file upload, including native file formats like AutoCAD and Rhino, but also some exchange file formats like STEP, STL, or IGES. And once you've uploaded your CAD model, the first step is what we call meshing. And it's actually about dividing one big volume you have into a lot of small cells. And later, we will only calculate velocity and pressure for the center of each subvolume. So in the end, you're dictating with your mesh the local accuracy of your simulation. And once this is done, you just need to define the boundary condition, which describe how your model is interacting with the environment. Then you can start the simulation. And finally, when the simulation is finished, you will get notified. And in this case, where we have a large simulation, it can take some hours. And then you can download the results if you want, but you can also visualize and analyze them inside our SimScale platform. And therefore, I would like to switch now. And I hope you can see my screen now. And This is just how SimScale is working. So I'm inside my web browser. This is standard Chrome browser without any plugins. And what I will do now, I will go to the dashboard. Sorry, I will go back. This is a project created by my colleague Christos. And I will just create a copy now. And that's what we call a public project. So he was using a public plan to create this project so everybody can access it. And yeah, now let's also take a look inside the project. And as you can see here, we have the geometry. And you can see he used different versions and played a little bit around with the geometry, because sometimes, for example, the geometry as a whole or something like this. So this is something where you at least need to invest some time, but with some experience, it's really an easy job. And then you can see the mesh here, so how the model was divided. And here you can see like that we used different size of elements based on the curvature of the geometry. And yeah, usually this is also very important and part of the job of the user to understand where we need a lot of elements and where not. However, once this is done, the next step is to set up the simulation. You choose like which solver you want to use. In our case, it's convective heat transfer. We'll talk about what this means in some seconds. And then we have different boundary conditions like the inlets here, the heat released by the occupants, the outlets, the windows, where we have heat transfer, the ceiling, where we also have heat transfer, the walls, where we have a different kind of heat transfer, and the floor. And once this is finished, you just need to start a simulation run. And then you can take a look at the convergence field or even at the 3D solution field. Yeah, and now on this slide you can see which boundary conditions we used. So as I mentioned, first of all, we used like different inlet and outlet locations. And for the inlets, we had, yes, the inlets are red and the outlets are green. We added a constant metabolic heat rate for the people, which are represented by this dummy geometries. And we used different insulations level and heat transfer coefficients for the ceiling, which is made from glass, for the glass windows, and for the walls. Yes. And now let's talk about some aspects of ASHRAE 55 which are important for the simulation. So what we're going to do is we will set up a flow simulation, and then we'll calculate PMV and PPD based from the simulation results. So what are we talking about? PMV stands for predicted mean vote, and it's a kind of, let's say, heuristic or artificial metric to quantify the comfort level of human occupants in a room. And the reason why we need PMV and we cannot just use the temperature is that there is a difference between the actual physical temperature and, let's say, the comfort temperature. And actually, if we think or we feel that it's comfortable depends on the combination of temperature and velocity. And this is something I think most of you can easily understand. It's something different to sit in the garden at 15 degrees if it's wind still and sunny, or if it's, you know, very windy. And also the PMV says that you need to include into your calculations the metabolic heat release by the participants, by the occupants, and also the insulation level of the clothings. And so this PMV is, in the end of the day, artificial temperature or something related to temperature would tell us like if for majority of people these conditions would be uncomfortable or comfortable. And PPD stands for predicted percentage of dissatisfied, and this is something computed from PMV, and it represents the percentage of uncomfortable occupants. And wherever PPD is below 10%, it's comfortable, and then the color is green, and if not, we have uncomfortable conditions. And we need these two metrics to, let's say, connect the simulation results with the ASHRAE standard. Now let's take a look on the case we've investigated. As I mentioned, there are a lot of reasons, a lot of different reasons to use simulator, a lot of different strategies for optimization. In this case, we want to focus on a very simple approach, which can be also applied at a very late stage of building design, which is to optimize the inlet temperature and flow velocity. And therefore, we have created at least 13 different cases, which are visualized here. So everywhere it's blank, we didn't run a simulation, whereas a plus, we run the simulation. So this case 1, for example, means that the temperature at the inlet is 30 degrees and the inlet mass flow is inlet velocity is 0.5 meters per second. And we have marked case 3 and case 1 because these are the two cases we are going to take a look at. And now let's take a look at the results. Just to make sure everybody knows about the scenario we are considering. So we are considering a winter scenario, which means we have an ambient temperature of 4 degrees Celsius. Inside we have these people, and every one of them is releasing 36 watt of heat. And through the windows we are losing 3 watt per meter Kelvin. Through the walls we are losing less heat, it's only 0.6 watt per meter Kelvin. The floor is quite cold with 13 degrees Celsius, and the glass ceiling has a heat transfer somewhere between the windows and the wall. It's 1.5 watt per meter Kelvin. And first of all, let's take a look and compare case 1 and case 3. And here you can just see the temperature at the walls, which give a good idea about the temperature inside the room. And as you can see, case 1 is much too hot. It's like over 25 degrees everywhere, like 1.5 meters, 2 meters above the floor. And in contrast to that, case 3 looks much better. And now we will try to find out what is really happening inside the flow field, and I will show you how to apply PMV and PPD. First of all, let's take a look at case 1. And remember, case 1 we had the higher inlet temperature of 30 degrees. First of all, you can see PPD, and it's quite obvious that actually everywhere except maybe the first meter from the ground level, people are uncomfortable. PPD is much too high. And if we now use a kind of slice through the flow field, we can visualize temperature and velocity field and some other fields. And first of all, what we can see here is that in case 1, the temperature at the ceiling is, it's quite low. Like we have on it low 23 degrees, it's fine actually. And the PPD compared to that is quite high, because now instead of temperature and velocity, we're taking a look at PPD and PMV. And as you can see, like nearly here there's a little bit comfortable. So it's like it's even a little bit too cold, but it's still below 10%. If we take a look at PMV, it looks also fine. But if we now go up to the second floor, you can see first of all the temperatures ranging massively higher, like up to 2 degrees. And if we now take a look at the velocity field, we can see that we have a very unhomogeneous flow distribution, and which is much worse. All the area is actually uncomfortable. There's a small bubble here where PPD is below 10%, but everywhere else it's at the range of 25%. And also PMV is much too high. So for the people, it seems like it's too hot. And if we now take a look at the highest floor level, again, temperatures are high, flow speeds are high, and the result is much worse. Beside of these two spots, here and here. And everywhere the PPD is too high, and actually there's just one person here which is in comfortable conditions. On this image, and this is something I really like, it's visualizing like which areas I have with a high PPD and PMV. And you can see that actually everywhere in all floors we have a large area where people will be uncomfortable. Now let's take a look at case 3. We have the same inlet and outlet positions. We have the same mass flow or inlet velocity. The only thing which is different is our inlet temperature. And again, let's take a look at first of all, at the PPD. And you can directly see that it's looking much better. It's a little bit off at the first level, but everywhere else it seems to be better. And if we now compare the temperature profile, and again we're taking a look at the first, second, and third floor, and actually this temperature and velocity are not so interesting right now, but what is interesting is PPD and PMV. And obviously now the first floor, the PPD is not optimal, but if we go further to the second floor, you can see that immediately things are looking much better, and actually now in the second floor the PPD is perfect and everybody is, let's say, in very good thermal conditions. And if we go up to the third slice, you can see that even here it's much better. Temperature distribution looks quite homogeneous, and, which is much more important, PPD again is in range everywhere. Yes, and this is a PPD representation and PMV profile for case number 3. And now it's completely different. There is just a small area where PPD is higher than 10%, and everywhere else the conditions are really perfect. And if we summarize this, like in this case we created 13 simulation runs, and it was like 1 hour of manual time preparing the CAD models and uploading everything. Then it took SimScale 4 hours using 96 cores to calculate all 13 simulations, and in total we used 4050 core hours, which means that the simulation on a dual core workstation would actually take 2000 hours. And first of all, this simulation helped us to find the best operating conditions, and this actually means that we were not only able to reduce massively the space the percentage of space with uncomfortable conditions. So if you compare the left and the right image, you can see that all this red stuff disappeared, and which is maybe also very important, by reducing the inlet temperature by 5%, we actually will save 10% of energy. Yes, thank you very much, and I think I'm done with my presentation, and now let's start to talk about your questions, and let's see if I can answer all of them. So there is the first question by Paul, and Paul wants to know, is it a good option to select the bottom of the domain as a wall instead of outlet? Paul, to be honest, I can't, I'm not sure if I 100% understood you correctly. So maybe you can specify your question a little bit more. In the end of the day, when let's go back to the slide, when we want to talk about boundary conditions, it makes sense to take a look at it. So, yeah, let's take a look here. So, you need an outlet wherever you have a physical outlet. And if you want to simulate what's happened if the outlet is at the bottom, you need to select this patch of the surface as the outlet. Christoph wants to know what have to be included in the internal geometry of the building, like furniture, and what can be omitted. That's a good question, Christoph, and it really depends on what you're doing. And I know that our customers, everybody's doing it differently. Usually what we suggest is at least to have all the internal walls and doors inside. When you, for example, already know that there will be a lot of big furniture, like massive tables. You can include them, but usually I would say you should simulate that state of the building, which is part of your job. And in the end of the day, it's just a question of core hours. We even made simulations where we had simulated some monitors on the desks, but from my experience, usually this level of abstraction it's fine. Konstantin wants to know if simulated smoke, if we can simulate smoke from the atrium. Yes, Konstantin, this is something we can do. And for this, we offer different options. Like, if you're only interested in the fumes, we would suggest you do a passive scalar simulation, but we also have a FDS early access program in the case you're interested in the actual fire. And if you're interested in this, we have a webinar about this on our website. Just check simscale.com/workshops-webinars. Okay, Paul described what this question was about when you talked about natural ventilation. Well, it depends, Paul. If you have an opening at the bottom or the top of your building, then you need to put an outlet there. But usually the openings, and that's a big difference, usually the openings in your building are not modeled as outlets in a natural ventilation simulation. The outlet boundary condition is only used for the ambient. If you want to simulate, and that's the next question by Christoph, for example, computers and servers, like if you have when you have server room, there we have also a dedicated webinar about that, which shows how to include the servers and how to optimize the cooling concept. Also just check simscale.com/webinars. Mushin wants to know how big the mesh for this case was and how many cells were used. I think this was a 10 million cells case and we used 96 cores. And Caroline asked if SimScale software runs online. Yes, SimScale runs only online, but you don't need to install anything. Just go on simscale.com, create an account in 5 minutes, and you can start to simulate. All right, it seems like I answered all the questions. Thank you very much for being here with me. It was a big pleasure. We will send you the recording, I think, tomorrow. And if you have questions, just reach out to me or to my colleagues from this user success team. Thank you very much. Have a nice evening and see you soon. Bye.